All right, good evening. Well, homework number 10, we're working with three what are called cyclic devices. So one's a heat engine, the second's a refrigerator or air conditioner, and the third's the heat pump. So we've gone over 2 out of 3, and this brief lecture is about heat pumps. With this lecture, I encourage you to have a sheet of paper to write down, at a minimum, the main equations and ideas about heat pumps. Feel free to pause every now and then. I will do an example at the end, and it'd be great if you pulled out your calculator and worked on it yourself. All three of these devices, with a little bit of work, are pretty easy to understand and give you a good idea about a lot of things that go on energy-wise in our world. All right, well, let's get at it. Heat engines. Heat pumps. Heat pumps. So basically, heat pumps are one way that these days we're using to heat homes or other buildings. So in general, if you have a building like here in Sacramento on a really cold morning, 70 degrees inside, 30 degrees outside, energy flows out of the home by heat. And we got to replace it if we're going to keep that building warm. How are we going to replace it? Well, historically, a lot of heating was done by wood, and the problems that came up with that are similar to the problems that we have now. There are several societies where they started to prosper, and they started cutting down all their forests to heat homes. And in some cases, those societies, once they cut all those forests, they just ended up perishing because you've got to have heat in order to survive. It's kind of interesting. Our code, for buildings, does not require that we cool. You can put up a building with no cooling in Sacramento, and the building department will say, hey, that's fine. Because strictly speaking, cooling's not that much of a health issue or a requirement for health, maybe for a nursing home or something like that. But heat, here in Sacramento, they're not going to let you put up a home and occupy a home unless there's some sort of heating system in there, because if it gets too cold in there, it truly is a health issue. Well, how does that relate to now? Now, the big issue that we're up against is global warming. Most heating for our homes is done with gas heat, and that produces carbon dioxide. So the various government agencies that monitor energy use in the environment are very concerned about that and thinking about what can be done instead. And it's a challenge, without doubt. The idea that the California Energy Commission here in Sacramento has, and that other people have that's being strongly promoted, is to heat homes with heat pumps. So just talking about that really quickly, what that would mean. Typical home here in Sacramento, when it's losing heat, that means it's losing about 200 BTUs per minute. Okay, that's a well-constructed home in Sacramento. 70 degrees inside, 30 degrees outside, it's losing 200 BTUs per minute. Most of that's through the windows, actually. Okay, so how are you going to replace it? How are you going to get heat back in without, say, burning wood or burning natural gas, which creates pollution and carbon dioxide going into the atmosphere? All right, well, the California Energy Commission's idea is two things. Okay, 30-degree air out here. Anything with a non-zero temperature has energy. So this air out here has energy. California Energy Commission's idea is that we're going to grab energy from that air. And somehow we're going to use that energy to heat our house. California Energy's second idea is that we're going to do it using a refrigerator. So we're going to take energy from 30-degree air, get it into our home to make us comfortable, and we're going to repurpose refrigerators to do it. Sounds a little bit crazy, but it's really pretty simple to understand. So let's switch over here and just take a look at a refrigerator. When you think of a refrigerator, you think of like that box that's in your kitchen. When an engineer thinks of a refrigerator, they think of a device that looks like this. So let's go through it really, really quickly and figure out what's going on. Okay, this right here, this evaporator coil right here is what actually does the cooling. So over here, at this point, the refrigerant, these lines represent piping that carries refrigerant. Okay, and at this point right here, refrigerant goes through a coil like there, and here, an evaporator coil, and it picks up heat. So you could have a 30-degree area in your refrigerator, and there's a coil nearby. This refrigerant right here is maybe about 10 degrees Fahrenheit. Okay, and heat ends up going in there. That's great. Okay, then what we got to do, we got to get that heat out of that coil. Okay, so what we do next is this process goes over to a compressor. Okay, there's power input to the compressor, and what that does is bumps this refrigerant from, say, 30 to a higher temperature. Typical would be like 110 degrees Fahrenheit. So up there it bumps it to 110 degrees Fahrenheit. Okay. Then after that, what ends up happening is we go through a condenser where the refrigerant gives up its heat, and it ends up dumping to your kitchen, where your kitchen is essentially 70 degrees Fahrenheit a lot of times during the winter. And then after that, the refrigerant keeps going, and it goes through a device called a throttling valve, where it drops in temperature and pressure and ends up at that 10 degrees Fahrenheit. So when your refrigerant's running, that's what's going on again and again and again and again. Is some refrigerant is actually going through here, picking up heat to cool, to get heat out of a 30-degree area, then going through a compressor to bump up its temperature and pressure, coming here through a condenser and dumping its heat, and then going through a throttling valve so it can do it again. Okay, well, hopefully you can look and see, hey, that's really similar to what we would need to do if we were trying to heat a home, okay? If we wanted to use 30-degree temperature air, okay? If we could pull heat out of a 30-degree air, okay, bump up its temperature to a high temperature so that it could dump its heat to our house, then we could actually heat our house using outdoor air. So that is, in fact, what a heat pump is. I'm going to erase the board right now and try to give you a little bit better idea on it by doing a little bit of work. So hang on for just a second, please. All right. Okay, so let's just first start with the verbal definition of a heat pump, okay? What a heat pump is going to do is pull energy from a source. I'll just write this down. From a low temperature source, okay? All right, and then it is going to increase the temperature of that energy. And how does it use it? Well, to do that, the most common way is with a compressor. And then finally, it's going to deliver the energy to a point of use, like our home, or some sort of space. All right, so and that is in short what a heat pump does. Okay. I showed you, a few minutes ago, I showed you like the compressor, the condenser, the evaporator, the throttling valve. It would be great if you understand that. But for purpose of this course, for our three cyclic machines, heat engine, refrigerator, air conditioner, heat pump, we want you to be able to do these circle reservoir diagrams, which just simply indicate the purpose and function of the machine without all the details. All right, so let's just go ahead and do that. I'm going to get a couple circle reservoir diagrams up there, and I encourage you, after you stare at them for a second, to copy them down, pause the video, and see if you can fill them in. So something I'm going to ask you to do on test 3, okay, is to fill in a couple circle reservoir diagrams to show me that you understand these different machines and their purpose. Okay, so I'm almost there. I'll pause in just a second. Okay, so I got two of them. Here. One is the circle reservoir diagram for a refrigerator, and there's a relationship between the refrigerator and a low temperature area, and the refrigerator in some sort of higher temperature area. For your kitchen refrigerator, this low temperature area is the area inside your box that we're trying to keep cool, and the high temperature area is like your kitchen. Okay, here's a heat pump, and there's a relationship between this heat pump and a low temperature area and a high temperature area. For a home heat pump, the low temperature area is the outside air from which heat is going to be pulled, and the high temperature area is your home where the heat's going to be delivered. Okay, what I want you guys to do is just take a second, and I've got 6 lines here, decide which direction the arrows are going. Are they going into or out, up, down? And then in addition, should they be labeled with Q's or W's to indicate what's going on? So I encourage you to pause for a second and just come back in a minute and look. So. Okay, refrigerator. Oh, that is what we did when we met on Monday. So what a refrigerator does is it pulls heat from a low temperature area. Okay, it does it by using work. There's power put into the compressor, and then it ends up dumping heat to a high temperature area. So that's the diagram for the operation of a refrigerator. Not conveying what's going on inside the machine, but what the overall purpose or function of the machine is. All right, I'm going to do the heat pump now. I encourage you to do it yourself before you actually take a look at my answer. Okay, first of all, heat pump. What does it look like? Okay, with the heat pump, what we're trying to do is deliver heat to some temperature, some area, like our home. Okay, how do we end up doing it? Well, we pull heat from some low temperature area, like outside air. What makes the machine do what it does? Power input to the compressor. Somebody has to take that compressor shaft and turn it to make the refrigerant do what it does, and the result is that delivery of heat. Okay, good. So there's the heat pump. Second thing is just to stare at the two diagrams and make some comparisons. Are they the same? Are they different? If so, how are they different? And if you look at them, you should say, hey, they're exactly the same. And that's exactly right. It's the same machine doing the same thing. There's just two main differences. One is the purpose. For a refrigerator, this is our goal. We're trying to pull heat out of a low temperature area, okay? Whereas for a heat pump, this is our goal. We're trying to deliver heat to some area. So same machine with two different purposes. Another distinction that we might have is for these machines, where's the thermostat, okay? And for a refrigerator, the thermostat's actually in the cabinet of your refrigerator. There's a thermostat in there, and if it gets too warm in there, the refrigerator turns on and actually pulls heat out. How about for a heat pump? Where would the thermostat be for a heat pump? And it's actually going to be in your home. The thermostat's going to be up here. And if it gets too cold in there, it's going to turn on and the heat pump's going to run. All right, good. So what's left to do? A couple of equations for problem solving. So very, very simple. So I'm going to erase the refrigerator one and just give you the equations over here on the left. Okay, so the first equation is our efficiency equation. So I'm just going to write that up there. What's our efficiency equation going to look like for this? Okay, so efficiency of a heat pump is the useful result divided by what we pay for. Okay, when we run a heat pump, remember there was a compressor that had to be powered, and what we pay for is the power to run it. So it would be this work input. What's their useful result? Why do we run a heat pump? We run a heat pump to deliver heat to our space. So if our efficiency is going to be our input, which is Wn, or W compressor, and by the way, those could have dots because they could be rates, and in the numerator, it's going to be QH, or heat delivered. Now, just like for a refrigerator, this efficiency is bigger than 1 a lot of times. More heat gets delivered than compressor work. So the COP is used instead, and COP stands for coefficient of performance. So a coefficient of performance of our heat pump is QH over Wn. And there is, let me just go ahead and box it, there is heat pump equation number 1. Okay? Just like for the heat engine, and also for the for a refrigerator or air conditioner, is a second equation that comes from conservation of energy. So let me put some numbers up here, which I won't copy down, but here might be some typical numbers. Okay, if we end up pulling 60 units of heat from some sort of space, a lot of times for some heat pumps that takes about 20 units of compressor work. All right? And this is energy that went into the refrigerant. This is energy that went into the refrigerant. And that needs to be dumped. So this number right here is 80. And those would be very, very typical numbers. Maybe a little bit exaggerated up here, but that's okay. And so what I'm saying is that QL, the energy pulled from our source, plus work in, the work of the compressor, is equal to the heat delivered. So that can be summarized by QH equals QL plus W. And of course, those can be rates. All right, QH is equal to QL plus W. All right, and those are our two heat pump equations. All right, so hopefully you have this circle reservoir diagram. If you look in the book, they actually use boxes for the heat pump because a lot of times a heat pump looks like a box, and that's a really good thing. But also be able to visualize it this way, and you have these equations. Quick example, and then we'll summarize it and call it good. All right, so let me just describe the example while I'm writing it down. Okay, let's say we have a house, and it requires 200 BTUs per minute heat. And that's because it's in the winter and it's cold and it's losing heat, it's losing energy, so we got to put some heat in. Okay, and let's say we're going to do it with a heat pump. We're not going to use it with a gas furnace. We're not going to use a wood burning stove. We're going to use a heat pump with COP 2.5. Okay. All right. So our two questions are the BTU per minute and horsepower requirement to run this heat pump, and the second one question is fraction of heat delivered that is free. Okay, so let me let you guys think about those questions, and what I'm going to encourage you to do first, you could just jump in and use the equations, but what I'm going to encourage you to do is to do like a circle reservoir diagram or do a diagram of a heat pump in a house before you get going. And I'm going to do the same myself. So give me just a second to catch up. So I'll show you in just a second. Okay, so there's my crude drawing. I got this heat pump and it's going to deliver 200 BTUs per minute to this house. How's it going to do it? Well, we got to put work in, and these are rates, so I'm going to put a dot on there. And what it's going to do is it's going to pull heat from some sort of low temperature source. And for heat pumps, that's the outdoor air. That's the outdoor air. Okay, then what are we trying to solve for in part A? We're trying to solve for the input requirement in BTUs per minute and horsepower. So you can use either equation, but hopefully you can see that the COP equation is good to use. So I'll write that down there. Hang on for a second. Okay, so there's my COP equation. I'm trying to solve it for W dot. So just with a little bit of algebra, I can rearrange it. So W dot is the heat delivered divided by the COP. So that's going to be 200 over 2.5. Okay, and that cranks through 80 BTUs per minute. So 80 BTUs per minute is the power I'm going to have to put into this compressor and to run this compressor. Okay, the next thing is really important is thinking, okay, well, how are we going to actually run the compressor? Maybe that's something we could just do ourselves. You know, part of the concern here is, you know, as a society, we're just burning a lot of fossil fuel that's creating a lot of carbon dioxide. So is there some other way we could power things? And 80 BTUs per minute, how could we actually power that? Well, that's where converting to horsepower is helpful. So 80 BTUs per minute, There's 42.41 BTUs per minute per horsepower. So I'm just going to do that at my calculator really quickly to try to get a feel for what that's like. Okay, and I'm getting about 1.9 horsepower. 1.9 horsepower. Okay, so 1.9 horsepower, and that's going to heat our home. Okay, so could we do that ourselves? No way. The most a human can sustain is about a 6th horsepower. So you'd need to get about 12 people cranking on that compressor actually to heat our home. So that may not be that doable. And that is part of the problem with what the Energy Commission is suggesting. How do we actually run heat pumps a lot of times? Well, we do it using electricity. And how do we get electricity? Well, we burn fossil fuel. But at the same time, the Energy Commission is right. I mean, there are other ways to create electricity besides burning fossil fuel. So maybe long term, this is going to be a solution that we're going to heat our homes using heat pumps. All right, finishing it off, it says fraction of heat delivered that is free. So what's going on with that? Well, if you think about it, okay, this Q.L here comes from the outside air. It's energy that is in the air that's pulled, okay? When you run a heat pump, okay, and if you ever put this in your house, you don't have to worry about the police coming by and saying, hey, you're running a heat pump. You're pulling the heat from the energy from the outside air. You got to pay. It's free heat. No one, it's the outside, our outside air at Sacramento is such a large body mass that a little bit of heat, a heat pulled to heat a home is relatively speaking small. So we don't have to pay for that. So basically what we're asking you to do in part B is, as a first step, figure out what Q.L is, and that comes from our conservation of energy equation. So let me write that down. Okay, so there's our conservation of energy equation. Solve for Q.L. Q.L is equal to Q.H minus W dot. Q.H is 200. W dot was 80. 200 minus 80 is 120 BTUs per minute. So in this picture right here, we got 200 BTUs per minute going to our home. 120 is pulled from the outside air and it's free. So the fraction that's free is 120 over 200, and that's 60%. So we're heating our home and 60% of the energy is free. All right, well that does it. That does it for heat pumps. I really think homework number 10 is less a matter of struggling and with really hard concepts, and more just a matter of putting in the time. It's very tempting to say, look, hey, these equations are very easy, and they are fairly easy, but the feedback I've gotten over the years teaching this class is, look, if I just take some time, try to do some sort of diagram that indicates the heat flows, it makes sense. If I don't, it's some sort of source of confusion. Anyway, encourage you to finish off homework number 10 for Monday. Please email me with any questions. Have a great rest of the weekend, and we'll see you next week. Take care.